Okay, we're looking at problem number 41 on page 507 from chapter 9. This one's going to be about creating a confidence interval, and all they have given us to work with is raw data. So if I need a confidence interval, I'm going to need, it's wanting to know about average time, so this is for means, so I'm going to need the mean. So to get the mean, I'm going to go to Stat Edit and go ahead and follow along, and we will put this in your calculator. I need to clear out what was already there. And then we will put this set of data in our calculator. So once you have this data in your calculator, then we will be ready to proceed by doing stat, calculate, 1var stats, and this is on list 1, and this will give me the summary statistics I need to start constructing a confidence interval. Okay, once I've done 1var stats, we have some summary statistics that our sample mean is 54.2. That's an estimator. This sample mean is an estimator of the population mean, mu, which is the whole thing we're trying to find the confidence interval for. This is the sample standard deviation, which is an estimator of the population standard deviation. That is the SX on your calculator. And then the sample size is, of course, 10. And then the degrees of freedom is always n minus 1. I am going to need degrees of freedom because since I have the sample mean, since they did not give me the population mean and I'm having to estimate it with a sample mean, I'm going to have to use a t-distribution with the appropriate degrees of freedom. I also want a 90% confidence interval, so I'm going to need to find my critical t-value that cuts off 90% of that interval. So a t-distribution is going to look something like this, where instead of being, it's still going to be, we're estimating the center as 54.2 based on my sample. I'm estimating the standard deviation of 3.68, but it's going to be a little bit heavy tailed because t-distributions always have heavier tails than the associated normal distribution. So if I would have had a normal distribution, let me sketch what that would have looked like. If I would have known sigma, I would have had a distribution that looked a little bit more like this, a little bit more centralized with less data in the tails. The t-distribution is always a little heavier in the tails, makes it slightly less concentrated in the middle. So the z is in green, the t is in red. Either way, when I'm cutting off the 90% edge of our data, I'm looking for the 0.9 that is in the middle, and that means I'm going to have I can use my calculator to figure out that it's 0.05 in this extreme. Now I've got two choices. I can reach for my table. And if you look for your table, if you look at the row that is 9 degrees of freedom, and the column that is labeled either 0.05 for the tail or 90% of the middle, it will give you the t critical value off your table. Or if you don't want to reach for the table, we can pull the calculator up, and we can do second distribution inverse t, because we're starting with a probability trying to get a t value. My tail area is 0.05. My degrees of freedom is 9. And then I'm going to paste that in. And it gives me negative 1.833. So that is going to be the answer. Whether you use the table or the calculator, it's really your preference. Some of the higher degrees of freedom, you can get a slightly more accurate answer with the calculator, but the table's available and does quite well for degrees of freedom of this size. So far, I've estimated the shape. I've estimated the center of my distribution with my x bar. I have estimated the the spread of my distribution with the sample standard deviation, and what I have not estimated that I keep trying to get at is the shape. Now, what shape do I need to know for this distribution? Need to know that the shape of my sampling distribution is normal. Yes, it needs to be approximately normal. So if I'm going to have an approximately normal sampling distribution, there are 3 ways to achieve that. So See, this is what takes forever on these videos. And then it's like, it's too big, so let's make it smaller. So, anybody got a suggestion for one of them?
Normal plot.
No, there's the best way.
Something that you're going to advise.
Okay.
30, which is 30 people.
Oh man, that got turned on. I'm gonna have to edit that out. Okay, so one way to know that the sampling distribution of X bar is approximately normal is that if n is sufficiently large. So if n is sufficiently large, that means, and our rule of thumb for that is an n value greater than 30. That means that the central limit theorem states that the sampling distribution of X bar is approximately normal. Any questions so far? However, since n is not sufficiently large, I can't go with plan A. I've got to move on to plan B. So plan B would be based on the shape of my population distribution. So if the population distribution is approximately normal, then the sampling distribution of X bar is approximately normal. So it would be really nice to know that. Unfortunately, in this case, I don't. So it gave me no information about the sampling distribution of X bar. So, about the shape of the population distribution. So plan A has struck out. It wasn't a large enough sample that I didn't have to worry about the shape of the population. B is struck out because they did not give me a graph, or they did not come out and tell me in the problem that the population was normally distributed. So now I'm on to plan C. So since I can estimate, just like I can estimate the mean from the sample mean and the standard deviation from the sample standard deviation, in a pinch, as a plan C, as a last resort, I can estimate the shape of a population distribution from the shape of the sample distribution. So I can say if the sample distribution is symmetric and has no outliers, then it's reasonable to assume that the population distribution may be normal. Then it is not unreasonable to assume that the shape of the sampling distribution, of the population distribution, should be saying, is approximately normal.
You do not have to say that it's unimodal as well. That's like given.
In an ideal world, unimodal would be nice, but sometimes with the shape of a sample, you don't necessarily have enough data to even determine a mode. And we'll see that happen on this one. We're going to have to go forward with plan C, and we're going to illustrate how to do this. One way you can try is you can try just a straight up dot plot. Let me sketch one of those. So if I go for the dot plot, the minimum value was 48, right?
Why don't you just use the dot plot calculator?
Maximum value was 60. Calculator doesn't do a dot plot very well. So if that's 48, that's 60, and then I can do 52, 50, 52, 54, 56, 58, and we're going to graph those points real quick. Okay, from my dot plot you can see what we just mentioned, that it's really hard to determine a mode. It's actually hard to determine a lot, and the problem is that it's really not an ideal situation to be determining the shape of estimating the shape of a sample from just 10 data points and trying to estimate what's going on with the population. It would kind of be like taking a random sample of 10 South Caldwell seniors and trying to use that as an image of what the entire senior class looked like. No matter how random your sample was, you couldn't get a good picture of the diversity of the senior class as a whole just from a sample that small. So in an ideal world, we'd be using a lot bigger data. However, in this class, since we're having to do statistics with the TI calculator, it kind of limits the amount of our data because it takes so much time to get it loaded. If you were doing this, if we were allowed to use a software package for the exam, you could upload a file of 50, 100 data points, and then you could get a lot better estimate of what it looks like. So basically what we're doing is we're looking more for glaring problems than beauty. I can also use the same thing to get a box plot. There's my minimum, there's my maximum. My median would be between the 5th and 6th data point. My quartiles would be about at the 3rd and the 8th data point. So your box plot would look something like this. And if that is what your box plot looks like, you could definitely say that this box plot would be symmetric, or at least approximately symmetric, with no outliers. So you could say, since my box plot is approximately symmetric with no outliers, it is not unreasonable to assume the population distribution is normal. Therefore, the sampling distribution of X bar would also be approximately normal. So if I am doing one of these problems on a Frappy, I have just probably completed one of the 3 major parts of a confidence interval. The first major part would be to give some kind of a graphical display, or in this case, to show the shape of the sample distribution, and to include a statement something like this statement here that talks about the shape of the sampling distribution being symmetric with no outliers. It is not unreasonable to assume that the population distribution is approximately normal. Even if they do not specifically tell you to check the conditions, it's important to always check the conditions for doing this confidence interval. Now, once I have that done, the next thing I'm ready to do is actually calculate the confidence interval, since I now have an estimate for shape, center, an estimate for spread, and I have reasons to believe that my shape is approximately normal. The general formula for a confidence interval is it's the statistic plus or minus the standard deviation, your critical value, times the standard deviation of your statistic. In this particular problem, here's going to be the formula. So that's the formula I'm going to use, X bar plus or minus my critical value. In this case, it's a T star. It's a T because I had to estimate sample standard deviation, and then everything I have there. So I'm going to need to plug in the appropriate numbers from the top of the page. So X bar is equal to 54.2. My T critical value I found was 1.833. Don't have to worry about the negative because of the plus or minus. The S value, 3.68, and the N value is 10. And then you can just put that in the calculator to get your actual confidence interval. Well, if I put the margin of error part, in, it gives me the 2.133. And then if I start with that, I can do the 54.2 and add on that value, which is a 56. And then I can also take the 54.2 and subtract that value. The advantage to putting in the calculator this way is you get the margin of error of 2.133, and you also get the interval bound of your confidence interval of 52 and 56.3. Now at this point, showing the formula with the substitution step and actually calculating your confidence interval, you've done 2 of the 3 parts worth of credit on this question. Checking assumptions with the first part, getting the intervals the second part. The third thing you must always do is interpret it in the context of the problem. So in this case, we would say we are 90% confident. Always introduce what confidence level you have. That the true, and look for the context of the problem. In this case, we're talking about the true flight time from Albuquerque. That's going to be fun to spell. We're just going to do that. New Mexico to Denver, Colorado is between 52.07 and 56.33 minutes.
This 4 minutes is really important.
Now, sometimes you can get away with stopping there, but it's a good habit to also tell what it means to be 90% confident. So we could say a confidence level of 90% indicates that if very many simple random samples of size 10 were collected from this population, the interval are approximately, I'd prefer to talk about it this way, approximately 90% of the intervals constructed would contain the true flight time. So this confidence level of 90%, we're making it clear that it's based on if I were to do this same methodology over and over and over again, the interval I would create would capture the true value 90% of the time. Please notice that we are not saying this one interval is accurate or not. We have no way of knowing the accuracy of this one interval we've constructed. Just if we were to do this a whole bunch, we know that about 90 times out of 100 we would capture the true interval. So the true mean flight time would be the population mean, yes. So we would be talking about the true population mean flight time. So the average flight time, not the time of an individual flight, thank you, but the average flight time. Anybody have any additional questions? If you were scoring this, that would be the third part, would be interpreting your interval in context, and if you were asked to, also talking about your confidence level. It's a good thing to practice talking about your confidence level on the Frappy if they don't ask for it. If you're not really confident that you're going to do it right, I don't know that I'd put it. If they just ask you to interpret the interval, you can usually get away with just this top part, but if they ask for you to interpret the interval and the level, you have to do the whole rigmarole. On a side note, several of you did have some people bring up the possibility of doing a normal probability plot to determine the shape. Back when I was checking my assumptions, I could use a normal probability plot. The way I could do that is I could do stat plot, and I would do turn my plot on, and then I would change it to the normal probability plot, which is the one on the end. If you're using a older calculator, it's the one on the lower right, and then that would be the data is list 1, and I would need to do zoom stat to zoom in on the normal probability plot. If you did a normal probability plot, you would need to sketch the graph of the normal probability plot, just like you sketch the graph of the box plot. But then you could say, instead of talking about the sampling distribution being approximately symmetrical with no outliers, you could say, since the normal probability plot showed a strong linear pattern, it's very reasonable to suggest that this sample came from a normally distributed population. So you would still, one thing that is important is that you do make it clear whether you're talking normal probability plot or box plot, that you have 3 different distributions. You have the sampling distribution, which is your data you have graphed here on the normal probability plot or the box plot we did earlier. Then you're using the sampling distribution to talk about the shape of the population distribution. And then once you're saying the population distribution is approximately normal, then you can say that the sampling distribution of X bar. So basically your 3 shapes are the one you can see, your sampling distribution, the one you wish you could see, your population distribution, and then the one we actually care about, the sampling distribution of X bar that all of our critical values are based on.
And it's not the distribution of each number, that's the distribution of the averages.
Yes. I had another student ask about why I'm still using a t-distribution if I'm going to all this problem to show that my sampling distribution of x bar is approximately normal. So here's my best explanation of that. What this is based on is the actual sampling distribution of x bar, which does need to be approximately normal. However, this sampling distribution of x bar is based on the true standard deviation, which is sigma divided by square root of n. Since we've had to estimate sigma with my population standard deviation, what I have is some form of a t-distribution, which is still centered in the same place, but it has heavier tails. This t-distribution, its variability is based on s divided by square root of n. Reason we care about the shape of the sampling distribution is it needs to be approximately normal. That way, because your t-distribution is going to be unimodal and symmetric. T-distribution, you can think of it as a distribution that would be normal except for it's too heavy in the tails. It's almost like a kangaroo. It would look like a normal animal, but its tail is too fat. A t-distribution would be a normal distribution, but its tail is a little too fat. So that's why it's important to know that the underlying sampling distribution it's based on is approximately normal. That way, even though it's not normal because the tails are too fat, it's still unimodal, symmetric, unskewed, balanced in the correct place, and everything else.